Thank you for the introduction and welcome to this presentation, The Fundamentals of Conducted Immunity Testing as per MIL-STD-461. The standard is issued and published by the US Department of Defense, USDOD, and it's considered a guideline that provides limits and test criteria for EMC testing of electronic and electrical systems and subsystems. The standard has a lot of tests which must be conducted. However, and due to the short time, we will only focus on 3 tests. We will first start with some general but important information regarding the standard. Then we will move on to the fundamentals of CS115 tests, and then followed by CS116, including live session, how to calculate the Q factor. And last but not least, we will then move on to CS118 test. Here you see the main product categories and platforms covered by the MIL standard 461G. There are 5 main categories. We have surface ships, submarines, aircraft, including Navy aircraft and Air Force. We have space systems and launch vehicles, and we have also ground equipment and platforms, including Navy, Army, and Air Force. Unlike commercial standards where you find terms such as surge, burst, dips, ESD, and so on, the MIL standard takes a different approach and set codes for each test. We have conducted emission tests which all start with CE followed by 3 digits, radiated emission tests which start with RE followed by 3 digits, conducted immunity starting with CS and 3 digits, and radiated immunity RS followed by 3 digits. Here an overview of MIL standard 461G emission and immunity requirements. There are 19 tests in total, depending on the platform or UT installation. So as you also can see, CS118 is a new test that has been introduced to the G version. The test is actually electrostatic discharge and is very similar to the commercial ESD test as per 61000-4-2, as we will see later on when addressing the CS118 test requirements. Here you have the requirements matrix, which can also be found in the standard according to the G version. As I said before, there is 19 tests, and as you can see, depending on the installation, whether, for example, on surface ship or submarine installation, you will have different test requirements. So green areas refer to applicable and mandatory tests to the platforms. Yellow refers to L, which means limited customer specific requirement. Let's take, for example, CE106 test. This test is specific to antenna interfaces, which means it is only limited to equipment that also have an antenna interface. Red S or S is only tested if it's explicitly specified in the specification documentation. So general configuration setup is similar to what you are seeing here. The test table height shall be between 18 to 90 centimeters. The ground plane shall be bonded to enclosure. The impedance shall be less than 2.5 milliohm according to the standard. All cabling shall be elevated above the ground plane by 5 centimeters using non-conductive support material. Individual cabling shall be separated by 2 centimeters from one another, minimizing, of course, crossover as best practice. Power cables, power leads shall be routed to the front edge of the test setup boundary for 2 meters. Let's now start with the CS115 test bulk cable injection. The CS115 is a fast transient test. The test was introduced to replace the RS06 chattering relay test. The old test was seen as being unreliable, unscientific, and not reproducible. So the CS115 gives the most important property of the chattering relay, which is the fast rise and fall time, and has defined pulse shape and calibration setup. which ensures reproducibility of the calibration and test results. The test is conducted on all cables, including power cables and entire power bundles. According to the requirement matrix, the test is applicable to almost all military platforms. So the CS115 is a rectangular pulse. The test level as per standard is 5 amps. However, there are some other military standards that requires more than 5 amps, like for example the Japanese standard. So it is recommended to have a generator that is able to produce more than 5 amps. The rise time and fall time is 2 nanoseconds or less. So compared to the commercial EFT test, the rise time is much faster than the EFT rise time of 5 nanoseconds, which makes these tests a little bit more severe. The repetition rate is 30 Hertz to ensure that the UT is enough tested, and the test duration is 60 seconds. So on the left side, you see the possible or from the standard allowed impulse form. As you see, due to the frequency response of some injection probes, which might fall off at lower frequencies, so the pulse supplied to the probe could sag in the middle part of the pulse. It is hence more crucial to use an injection probe with good response at higher frequencies to produce the required rise and fall time. On the right side, you see as an example a real measured impulse with EMC partner coupler or injection probe. So the frequency response is good at lower as well as at higher frequencies, which allow to maintain the amplitude stable over the entire impulse during 30 nanoseconds. So moving now to the CS116 test, damped sine wave on cables and power leads. The CS116 test simulates cable resonances induced by the platform where the equipment is installed, or also caused by an external event like lightning strike on the installation platform, for example. The test is generally applied to 6 frequencies in the range between 10 kHz to 100 MHz, and the test is like the CS115 applicable to almost all military platforms, systems or subsystems. So the test levels start at 100 milliamps level at 10 kHz, increasing at a rate of 20 dB per decade to 1 MHz. The test level is increased to 10 amps between 1 MHz and 30 MHz, and then decreases at rate of 20 dB per decade to 3 amps at 100 MHz. If there are other frequencies that are known to be critical to the equipment installation, tests shall be also performed at these frequencies. The repetition rate is 2 Hz for all frequencies, and the Q factor is an important quality factor, or also called dampening factor, which is relevant for calibration and shows how quickly the waveform is dampened. The Q factor value must be between 10 and 20. So let's stay by the Q factor. The Q factor is calculated to ensure that the proper energy is contained in the damped wave. So here you see the formula used to compute the Q factor. IP is the first peak current, which represents 100%. IN is the peak current at cycle closest to 50% of the first peak, as you can see on the slide. So stable systems are able to produce the 50% peak always at the same cycle, which makes the calculation much easier. And N is the number of cycles. Since the quality factor is both positive and negative peaks of significant value regardless of the polarity of the first peak, there is no requirement to perform testing in both polarities. Either polarity is actually enough. Some test systems use a damped cosine wave instead of damped sine wave. This is permitted by the standard. Many customers prefer the cosine wave because it is more severe due to the fast rise time on the leading edge. Hence, EUT weak points can be detected with the cosine waveform, and due to the possible distortion of leading edge, the first peak shall not be used to determine the Q factor value. Instead, the next half negative peak shall be used. This is also applied to the negative peak closest to 50% of the first negative peak. However, if you have system that produce cosine and Q factor is within tolerance of 10 to 20 using the positive peaks, so it is also permissible to use it. So let's switch now to the live session to show you how to calculate the Q factor. So this is the typical calibration setup for CS116. We will need a generator, in this example, the MIL-MG3 with the right plugin. We will also need an injection probe or coupler, and then we will need a calibration fixture with the 220 dB attenuators. The coupler is, of course, connected to the generator, and then of course, we will also need a DSO in order to record the waveform and also for the calculation of the Q factor. In this example, we have a Rohde & Schwarz RTM DSO, and also we will need the TEMA 3000, the automation software for the calculation of the Q factor. So now we need to start a calibration or to start a test in order to capture the waveform on the DSO. Let's then do that. Then the waveform, so normally we have then 10 kilohertz, 100 kilohertz, 1 megahertz, and 10 megahertz. So in this example, we will go with 10 megahertz. The level selected is as per standard 10 amperes, and then the polarity is a positive polarity. So the time is the test, so we can just reduce the test to 30 seconds, and the repetition is 5 seconds in this example. Now we can start the test. So the next step is to enter the 3 parameters for the Q factor calculation in the DSO. So as I said before, now we have captured the waveform at 10 megahertz, and then now we can set up the 3 parameters for the Q factor calculation, which you can see here. We need the setting of 3 parameters. So the first parameter represents the peak value measured by the DSO on channel 1, which is this one. Then the second one is represents the peak value of current measured by the DSO at the 4th peak closest to the first peak, which is in this example, as you see here in the gate, is the 4th one. And then we need also the frequency, which is 10 megahertz in our example. So now we can move on to the automation software. In this example, as I said before, it's TEMA 3000. Let's start the software. So as you can see here, the generator is already connected to the software. It's already online. And first of all, we need to learn or store the setups we have already done with the DSO. For that, we need to go to DSO, and then you can see the Rohde & Schwarz DSO is already connected to the software. Then now we can learn the new setup or just replace it because we have it already, and then close. So the next step is then to create a single test. To spare a little bit of time, I have already done or stored the single test. We can just open it, open a test. So the generator is already connected to the single test and also linked. And then we need then to go to this O trigger in order to enter the formula for the Q factor calculation. So when we go to add, we have two settings there. The first setting is first store the screenshot when on every test or on every impulse, we need to take a screenshot. This is the first one. And then the second one is do a measurement on every impulse in order to calculate the Q factor. So in this case, we have the trigger is on every impulse, and the action is do advanced measurement, and then just enter the formula we have seen in the presentation already. So this is the formula. And once the formula is entered, you can then click on OK. And because we have now two take screenshots, we need only one. We can then delete one. And then run the test. So you see here, the waveform is recorded, and the Q factor is also automatically computed. Then we need just to wait until the test is done, and then we can generate a report. So now the test is done, is finished, and then we can either generate report wizard with wizard or then only a quick report. So we go to quick report, and then as you can see, here's the final report for this test or calibration. And then you can see in this table, the Q factor is also automatically recorded, or the values of the Q factor are recorded, and also all screenshots. And that's it. So you can see how easy it is to, in this case, calculate the Q factor using the right setup. And this setup you need only to do once, and you can store it in the automation software and use it every time you want to calibrate or calculate the Q factor. So thank you very much. So this was a short and practical introduction to the calculation of Q factor. Let's now briefly talk about the calibration and test procedures of both CS115 and CS116 tests. So these are the steps for CS115 verification and test method. The pulse must be verified prior to each test. First, the pulse generator parameters, rise time, pulse width, and repetition time must be adjusted. Then the pulse amplitude is increased gradually until the level of 5 amps is reached. However, professional generators are able to directly set the test levels to 5 amps, and also no need to adjust the rise time and the pulse width. The waveform parameters are verified, the pulse and generator settings are then recorded. After the calibration, the test can be performed. It is recommended to set the generator to minimum test level and then gradually increase the test level to prevent EUT damage during test, and whenever a disturbance is noted, the threshold of the test level is then documented. All steps are then repeated for each cable bundle. And these are the calibration and test steps for CS116 test. Before calibration, the equipment must be turned on to allow sufficient time for stabilization, and the waveform verification is quite similar to CS115. The amplitude of damp sign generator is gradually increased until the appropriate peak current level is reached. The test generator settings are recorded and the waveform parameters are verified for amplitude, frequency, and damping factor Q. This is repeated for each test frequency from 10 kHz to 100 MHz. So here you see the test setup for both CS115 and CS116. The test setups are straightforward and quite simple. Both calibration setups are similar. The injection probe is placed in the calibration jig. The 20 dB attenuators are connected to the jig on both sides. The coupler is connected to the generator, and also the DSO is connected to the probe or coupler using 2 additional 20 dB attenuators to protect the 50 ohm input of the DSO, since the test levels are quite high and could damage the inputs of the DSO without protection. Moreover, an automation software is highly recommended in order to compute the Q factor automatically and very quickly, as we have seen in the live session. The test setup can be performed as shown in the diagrams. The injection and monitor probes are positioned around a cable bundle interface in an EUT connector. The monitor probe is placed 5 cm from the connector, and the injection probe 5 cm from the monitor probe. For CS115, the calibrated test signals is gradually increased, as I said before, until the test level 5 amps is reached, and the test is conducted for 1 minute. For CS116, the calibrated test signal is applied to each cable or power lead of the UT at a repetition rate of 2 Hz at max for a period of 5 minutes. Moreover, to avoid overcurrent testing of low impedance cables, it is recommended to gradually increase the signal until either the generator's calibration setting or peak current test level is reached, whichever is less. Let's now move on to the CS118 ESD test to understand where ESD does come from. So let's first of all start with some very basics of static electricity we see in our everyday life. When you rub a balloon or a comb on your hair, electrons move from the hair onto the balloon, so the balloon becomes negatively charged and the hair is left with positive charge, and that's why the hair is then attracted to the balloon. This separation of charge is the reason for the collection of effects that we call static electricity. Another typical example of ESD occurs when walking on a carpet and then touching a doorknob, for example. the human body becomes electrostatically charged due to the friction with the carpet, and the charge then jumps to the metal doorknob. This causes a small spark and possibly an unpleasant shock. The body can actually be charged up to 35,000 volts. The CS118 test is used to verify that electrical and electronic systems with human-machine interface, HMI, can withstand electrostatic discharge, and the test is only performed in powered-up state. Explosive devices are excluded from this standard. For example, munitions are covered under standards such as MIL-STD-461. The CS118 test is, as I said before, based on the requirement of the commercial ESD. On the left side, you see the E-state generator specification, and on the right side, the corresponding impulse characteristics. Test levels are up to 8 kW for contact discharge and up to 15 kW for air discharge, whereas the ESD impulse verification is only conducted at 8 kW in contact discharge mode. RC network used for this test is a standard 150 picofarad, 330 ohm, like the RC network you know from the commercial ESD. The output voltage during calibration must be within 5%. So now let's have a look at the ESD impulse on the right side. As I said before, the calibration is done at 8 kV. The rise time is defined as the time from 10% to 90% from the peak value, and must be between 600 picoseconds and 1 nanosecond. The first current peak must be at 30 amps with tolerances of 50%. The second peak is measured at 30 nanoseconds and must be 60 amps. And then the third peak is measured at 60 nanoseconds and the value is 8 amps. So how is the ESD verification is performed? The standard requires two verification setups. The first one is the discharge current verification using 2-arm target, like you see on the left side, and an oscilloscope with at least 2 GHz bandwidth in order to capture the fast rise time of the impulse. The second method is using a voltmeter to monitor the voltage of ESD generator, like the one you see on the right side. And unlike commercial ESD, the verification is performed prior to each test. Just briefly, how the ESD test is performed as per MIL-STD-461G. So 5 positive and 5 negative discharges are applied to each UT test point. The test points are also defined in the standards. For contact discharges, the ESD simulator tip is directly placed on the test point and the discharge is applied. Very simple. However, air discharges is a little bit different compared to the commercial approach. As per MIL standard, the operator shall start a distance from the test point where no discharge occurs and slowly move the tip towards the test point at a rate no faster than 0.3 meters per second until the discharge occurs, and in between discharges the residual charge shall be removed from the test point by, for example, grounding through 1 mega ohm resistor or just waiting until the charge dissipates. The test is repeated for each applicable level as defined in the standard. Thank you for your attention and looking forward to your questions.